Hi all, welcome to 13th lecture of this lecture series named Unconstrained Optimization, and today we'll discuss Steepest Descent Method. We touched this topic in our last lecture, but today we'll analyze it more and try to look at it from various directions. So before starting the lecture, let's just revise what we looked in the last lecture briefly. So let's say we have a contour map as shown in this blue color, and gk is the xk is the current iteration point, and gk is the corresponding gradient direction at that point. So the corresponding descent direction set is denoted here by this green this green span, and any direction in this area will be a descent direction. So for example a dk, and it can be represented as minus ak gk, where ak is a symmetric matrix. Now a special case is when if is the steepest descent direction, in which ak is an identity matrix and dk uh, dk is given as minus gk, and this is called steepest descent. Why this is called steepest descent? Because if if we approximate the function as a linear function around xk and try to find a direction in which this linear function decreases the most, it is this direction, that is minus of gk. So that is why it's called steepest descent direction. Now we also discussed the algorithmic form of the steepest descent direction. Let's look at it once. So as in the case of in the case of the algorithms, we first initialize the initial value of the variable. We define a epsilon constant, which is a small value used in the stopping condition of the algorithm, and we also initialize the iterate to 0. Now we start a loop and we write a stopping condition such that the norm of the gradient is if it is greater than the epsilon, which is a small value, then the loop should continue. Now in case of selecting the descent direction, we select it as minus of gk. This is uh, this is the main step in steepest descent direction. The rest of the algorithm is the same. Once we have got the descent direction, we now choose the step length alpha k, and it is chosen such that there is a decrement in the function value at xk plus 1, and alpha k should follow Armijo-Wolff's condition, or maybe Armijo-Goldstein condition. Then we update the point xk plus 1 and update the iterate, and this loop continues till the stopping condition dissatisfies, and at the output, and the stationary point is given by xk. Now please note that in the step 2a, in the step 2b, um, the elaborate algorithm has not been shown here, but while using the Armijo and Wolff's condition, you can either use backtracking line search, or if you don't want to use the inexact line search, you can use exact line search as well. Both in the both the case, the algorithm remains steepest descent algorithm, because the main step in steepest descent direction is selecting the descent direction equal to minus gk. Now that we have a fair idea of how the steepest descent algorithm works, and we know about its structure, let's look at it in a much deeper way, and let's look at the convergence of the algorithm. So now let us look at the convergence of the steepest descent method, especially for the quadratic case. Convergence of steepest descent method quadratic case. All right. So we'll check how fast does the steepest descent converge if we have a quadratic function to optimize. So consider the problem. Minimize x over x belonging to Rn fx, where fx is defined as a generic quadratic function which can be given as half x transpose hx minus c transpose x, where h is a symmetric positive definite matrix. All right. So what is the gradient of this function? So delta fx is equal to, let's say it is gx. It will be hx minus c. All right. And because it's a quadratic function, it is very simple to calculate the optimal point, which is x star is equal to h inverse c, because for a quadratic function there is a one single global and local minimum which happens at gx equal to 0, and you can get hx minus c equal to 0, which means x star equal to h inverse c. This is what we get here. All right. So for a quadratic function, we already know the optimal point. We just want to analyze how fast does this algorithm converge to this optimal point. So what we want is, how does steepest descent algorithm perform if applied to fx. All right, this is what we want to see. Now we'll make one assumption that the way we choose step length is by exact line search. So we assume that exact line search is used in each iteration. This is because for a quadratic function, it gives a very good equation or the expression for the step length if you use exact line search. You can also use inexact line search, but exact line search will give you a very good closed form expression for the step length. That's why we are using it. So if we are using exact line search, the question is, what is the step length? Step length alpha k at iteration k. Alright, only then we will be able to see if the algorithm is converging or not. So we have to find the expression for alpha k. So fx equal to half x transpose hx minus c transpose x, gxk equal to hxk minus c. Now phi alpha is given by fxk plus alpha dk, right? And because it is a steepest descent method, dk is equal to minus g of k. So this becomes f of xk minus alpha gk. Alright. Now that we want to do exact line search, so what is exact line search? Exact line search is given by alpha k is equal to argument. We try to solve one more optimization problem over alpha, and we try to minimize phi alpha. Alright. So what is psi dash alpha equal to 0? This will give us the argument of, like, this will give the value of alpha for which psi alpha is minimum, right? So now this is true because f is quadratic, which means psi alpha will also be quadratic, right? Because f is quadratic. All right, and because phi is quadratic, its minimum, there is only one local and global minimum, and it occurs when the gradient is 0. All right, so this should give us the value of alpha in exact line search. So fk delta f xk minus alpha gk transpose dot minus of gk. This will be the grade. This will be the differentiation of psi with respect to alpha. This should be 0. All right. Now, what is gradient of f? It is h of xk minus alpha gk minus c transpose minus of gk. This should be equal to 0, which means hxk minus c minus alpha hgk transpose gk. Minus goes on the other side. Alright, till now it is clear. Now we know that hxk minus c is what? Gk. From where? We had already seen this. Alright, so we are using this relation here. Alright, so gk minus alpha hgk transpose into gk equal to 0. Alright, and if you try to solve this, what you'll get is alpha equal to gk transpose gk upon gk transpose hgk. This is the step length for steepest descent method and exact line search. Alright, now we can write the update rule of x. What is the next point? That is xk plus 1 is equal to xk minus alpha k. So what is alpha k? Gk transpose gk upon gk transpose h gk into gk. So this is the update rule now. Okay. Now this we try to calculate what the step length would be. Now we want to answer the question, at what rate does xk converge? So what is the rate of convergence of xk? How fast will converge xk to the local minimum? This we want to know. So let's first define, just reiterate what our function was. So fx is defined as half x transpose hx minus c transpose x. Alright, we also saw what will be g of x. It will be hx minus c. Right, and we also saw that equating gx equal to 0 will give us the local minima or the global minima of this quadratic function, and it is equal to x star equal to h inverse c, which means that hx star is c. So we can replace c with this value. Okay, now to do the analysis further, to check the rate at which xk converges, we'll define an error function. Let's define E of xk, which is given by half xk minus x star transpose h xk minus x star. Okay, this is the error function that we're looking at. Please note that error function is always greater than 0, because if xk is not equal to x star, for x equal to x star it is 0, but for all other values of xk it is greater than 0. Why? Because h is symmetric positive definite. Alright, so now we'll use this function. This will simplify the analysis a lot, so we'll use this function for analyzing it further. Now if we simplify exk, please note that E of xk can be written as, if you'll simplify this term, what you'll get is fxk plus half times x star transpose h x star. This is and we have used the result x star x is equal to c here. All right, which we saw here. Now you can see this is a constant. This is a constant value, and which means the minimization of fxk is same as minimization of exk, because they are different. They differ only in the constant term. Okay, so if we are looking at the minimization, the minimum value of fxk will occur at the same point as e of xk. All right. Now let's just simplify this this expression by assuming yk equal to xk minus x star. So by this we are just trying to shift the origin to x star, kind of, and which means h of yk will give us hxk minus hx star, which is equal to hxk minus c, which is actually equal to g of k. Alright, so implies that h of yk is g of k. Now we'll just write the result that we discussed earlier, that minimization of fx will be same as minimization of ex. Of ex. Alright, why? Because they are different, they differ only in the value of constant. Okay, let's move ahead. So we have already shown in the previous question that we answered, what will be the step length. So let's just write it here. So xk plus 1 is xk minus gk transpose gk upon gk transpose h of gk times gk. So this is the update rule for steepest descent method and exact line search. Okay, exact line search. This is the update rule. Now let's look at what will be the relative decrease in E of xk, by which I mean E, by which I mean that if we shift from xk to xk plus 1, what will be the relative change in E of xk. So it will be given by E of xk minus E of xk plus 1 upon E of xk. Alright, so here E of xk is on the left hand side of the subtraction sign, because E of xk is larger. The error is larger when xk is at xk than at xk plus 1. Right, now let's simplify this. So xk minus x star h to xk minus x star minus xk plus 1 minus x star h xk plus 1 minus x star divided by yk transpose h yk. So here in the denominator I have written yk in place of xk minus x star, because here we don't need any simplification, but in the numerator we'll need to simplify this expression. So you can do it yourself. You can pause the video here and try to figure out what the numerator will be. I'll just write the result down, and it will look like 2 alpha k gk transpose gk minus alpha k square gk transpose h gk. This is what it will look like, and you can do it yourself. Divided by yk transpose h yk. So alpha came from putting the value of xk plus 1. This is where alpha k comes into the picture, and rest of the things will get subtracted, because xk plus 1 has xk in it and alpha k gk minus alpha k gk in it. Now let's put the value of alpha k in this, which we got from exact line search. So substituting alpha k equals gk transpose gk upon gk transpose h of gk if you try to put it in this expression, the result that you'll get is, you can do it yourself. I'm just writing the final result down here. U of xk, and it will be gk transpose gk gk transpose h of gk and gk transpose h inverse of gk. Okay, so this will be the result. This will be the relative decrease in the error function, but still it does not tell us anything qualitative about how the error is decreasing or how the xk will converge. So for making sense of this result, we'll need to use one inequality, one result called Kantrovich inequality. So let's define what is Kantrovich Kantrovich Inequality. So it is Kantrovich inequality. I'll just formally define it and then explain it to you. So let H belong to some n cross m. Let be n cross m. It be a real n cross m matrix. N cross n. Be a symmetric positive definite matrix and let lambda 1 and lambda n be respectively smallest and largest eigenvalue of H. Then for any x not equal to 0, x transpose x whole square and x transpose h x and x transpose h x inverse h inverse x is greater than equal to 4 lambda 1 lambda n upon lambda 1 plus lambda n whole square. So this is the Kantrovich inequality, that if we have a symmetric positive definite matrix H and lambda 1 and lambda n are its smallest and largest eigenvalue, then this inequality holds. And if you look at the expression, the left hand side of this looks a lot like this here. So we can use this inequality to get some bounds on the relative decrease in error. So using this inequality, we'll not derive this inequality, we'll use it at a result. So using this inequality, the relative decrease in error function can be written as, so I'll just first copy this part here. Alright, this is the result, which can be written as greater than equal to 4 times lambda 1 lambda n upon lambda 1 plus lambda n whole square. Alright, and if you simplify the expression, you can find that e of x k plus 1 can be written as less than equal to lambda n minus lambda 1 upon lambda n plus lambda 1 whole square times e of xk. So you get a bound on the error function in the next iteration given the error function in the current iteration. So it will be always smaller than some constant times the error function. So it will, because this is always a positive fraction, because this is positive fraction, exk is a decreasing sequence. Alright, because it is always less than something which is less than 1 multiplied by the current error, hence it is a decreasing sequence. So e of xk is a Why decreasing sequence? So why is this a positive fraction? Because you can see on the above there is a subtraction of two numbers, and here there is an addition. So this whole fraction will always be less than 1, whatever the values of lambda n and lambda 1. We also know that lambda n is greater than lambda 1, so that is the case. So when that happens, this will always be less than 1, and a square of a number less than 1 is always less than 1. So this is a positive fraction. So by this analysis we can say that exk is a decreasing sequence. So E of xk tends to 0. Now E of xk tends to 0 means that big expression xk minus x star h xk minus x star half, this tends to 0. Now this, because h is positive definite, this can only tend to 0 when xk is equal to x star. Alright, this goes to 0, then only this whole expression can go to 0. So these two expression help us say that xk tends to x star. Alright, eventually, because h is positive definite. Now let us look at some observation that we got from this analysis. So what are the observation that we got? So with respect to E, to error function E, the steepest descent method so before I continue, so till here we have shown that xk converges to x star. So the algorithm, the steepest descent method, in steepest descent method xk converges to x star, especially for a quadratic case. Okay, so now let's continue with these some observation that we made. So with respect to E, the error function, the steepest descent method converges linearly. Converges linearly with convergence rate no greater than lambda n minus lambda 1 upon lambda n plus lambda 1. So yeah, so this we can see from this relation. This will help us determine the rate of the convergence rate of the algorithm. So it converges linearly with convergence rate no greater than lambda n minus lambda 1 upon lambda n plus lambda 1. So the convergence rate will depend upon the eigenvalues of the H matrix or the Hessian of the quadratic function. It will depend upon that. So also the actual convergence rate depends upon x naught. So the actual convergence rate will depend upon x naught. So actually if how fast the algorithm converges will depend significantly on what is the initial condition that you choose. Now let's define a something something related to these eigenvalues, because they play an important role, right? So let's define something related to them. So define the condition number of H R is equal to lambda n upon lambda 1. So we define a condition number R, which is the ratio of largest eigenvalue to the smallest eigenvalue of H. Okay. Now we can say that convergence rate of the steepest descent method depends on the condition number of H. So we saw that, right? If it is circular contour, the steepest descent method just converges in one step, right? So if R equal to 1, which is circular contours, then convergence in one iteration. So it converges in one iteration. All right. But what if R is very, very greater than 1? It's not closer to 1. It is really large. We have elliptical, like highly elliptical contours, and convergence is really slow. And this is the observation that we got in the examples that we looked in the last lecture, right? So if we have circular contours, steepest descent method just converges in one step. But if we have very highly elliptical contours, it takes a lot of steps. It is highly slow. So this is the reason why that happens. Now, this was analysis for non-quadratic functions, but just to let you know, for non-quadratic function also you can use the same algorithm. For non-quadratic functions, you can use the same algorithm, and the rate of convergence to x star H to x star please note, in quadratic case H is constant. So H is a constant matrix. So this rate is a constant, right? But for a non-quadratic function, H will change at every xk. Hxk will be different as from hxk plus 1. All right. So all the analysis that we did was for quadratic case, and we said that it depends upon the condition number of H, because H was constant throughout. But for a non-quadratic function, it may not be constant. So for this, the rate of convergence to x star depends on the condition number of hx star. So basically Hessian at the optimal point. Okay, it is there. The condition number of this matrix will determine the convergence for a non-quadratic function. All right. So this is how we analyzed the steepest descent method. We'll end it here, and we try to see if we follow exact line search, what will be the step lengths. We also saw the convergence of xk to x star. How does it converge? How fast does it converge? We found it is linear convergence. with linear convergence with the rate of convergence depending upon the condition number of H, and we then observed certain points and we saw why steepest descent is faster in circular contours and slow in elliptical contours, and we also saw what how the rate of convergence will be dependent for non-quadratic function if we use the same algorithm. Now moving ahead, let's look at the next section. Let's write down the learnings from the previous section here. So the problem that we were trying to solve was consider the problem to minimize fx, which is defined as some quadratic function half x transpose hx minus c transpose x, where H is symmetric positive definite matrix. Symmetric positive definite matrix. Alright. Now, the learning from our previous section was condition number is very important. So, condition number of the Hessian matrix H controls the convergence rate of the steepest descent algorithm. It controls the convergence rate of steepest descent algorithm. All right. And if the Hessian matrix is I, or identity matrix, we'll have faster convergence. So faster convergence if Hessian matrix is identity matrix. Now we can, one idea comes to our mind when we see that steepest descent algorithm converges in one step for circular contours and takes a lot of steps for elliptical contours. So for circular contours it is it converges in almost one step if you use exact line search, and for elliptical contours it takes a lot of steps. All right, so can we transform the coordinates in such a way that can we transform the coordinates in such a way that we can transform it from circular to elliptical to circular, and hence we get the faster convergence? Can we do that? Let's see. So here are the circular contours. I'll just make the axis. And here are the elliptical contours. All right. All right. Alright, so let me draw axis for this as well. Alright, so can we transform the coordinate from elliptical to circular and hence get faster convergence? That's the question. So here the quadratic is given by half x transpose hx minus c transpose x. If we ignore this term, this is the main h term. Can we, so I hope you the linear algebra course that you might have taken, in that you might have learned the Cholesky decomposition, in which H can be written as LL transpose, symmetric positive definite matrix H can be written as LL transpose, which means it if we transform X appropriately, we can write it as Y transpose L inverse L transpose L inverse transpose Y, and this can be converted into half Y transpose Y. Here the H is identity matrix and hence its condition number is 1. We have circular contours and we'll get convergence in one step. So this is the idea. Let's look, can it be done? So let's write the steps that we took already. Let H equal to L transpose. Please note here L is a triangular matrix, lower triangular matrix, and in your linear algebra course you might have learned that a symmetric positive definite matrix can be decomposed in this way, where L is a lower triangular matrix. Okay, so be the Cholesky decomposition of H. All right, now we'll define a transformation Y equal to L transpose X. So we are transforming X to Y through this expression. Okay, so now the function fx is transformed to the function hy by the following. So hy is equal to defined as f L inverse transpose y. All right, so this is the new function hy. Now let's see what the definition will turn out to be. So f L inverse y, it will become half y transpose L inverse h L inverse transpose y minus C transpose L inverse y. Right. This will be the thing. Yeah. So now we know that H is LL transpose. So half Y transpose L inverse L transpose L inverse transpose Y minus C transpose L inverse transpose Y. Now we can see this becomes identity, this becomes identity, and the function becomes half Y transpose Y minus C transpose L inverse transpose Y. Alright. We can see here that two things we can see here. First thing is the Hessian matrix of hy is identity. So and the second, its identity. So let's apply the steepest descent method. Steepest descent method. So yk plus 1 equals yk minus delta h yk. Here we have, just to simplify things, step length is 1. Okay, we are assumed the step length to be 1. Now this can be written as yk minus delta f L inverse transpose yk into L inverse. All right, so this can be written like this, and if we multiply by L inverse transpose on both sides, so yk plus 1, L inverse transpose yk plus 1, let me write it with different color. So L inverse transpose equal to L inverse transpose yk minus L inverse transpose L inverse delta f L inverse transpose yk. All right, so if you can see, this is xk plus 1, right? So xk plus 1 is equal to, this is xk minus h inverse, this is h inverse here, into delta of fxk. All right, so this is the new formula for steepest descent, or maybe you can say whatever the modified algorithm this is. If you transform the coordinates such that the elliptical contours convert to circular contours, this is the new algorithm that we get. And if you see, what this means is usual gradient direction, which is this gradient direction, is deflected by h inverse. So it's just rotation of h inverse, etc. Is added to this gradient direction. So this algorithm we'll learn in the next lecture, and this algorithm is actually you might know about it. It's the Newton algorithm, and we'll learn about it in the next lecture. We will know about, we'll discuss how we why this is useful, and what were the motivations for the initial development of Newton's algorithm, and how is it better than steepest descent. So we'll end this lecture now. Until then, thank you.